So yeah, hi. I'm pretty happy that a lot of people showed up. I was a little bit scared because it's the after lunch session and there are some some nice talks at the moment. So pretty happy that all of you are here. So my name is Franco. I'm from TACEO, and at TACEO we like to talk a lot about MPC and collaborative-SNARKs, of course, also. And that's what we are going to do about the next hour. So to participate in the workshop, I prepared a GitHub repository. Scan the QR code if you want to participate with your laptop. I'll keep it there for 1 minute or so. In the meantime, I'll tell you, and maybe also if you want to check it out, there's like a README with installation instructions that you need to do. I also prepared a Docker image, so you can also just run it with Docker where everything is already set up. Because I also usually don't like if I have to install 7 tools for a workshop and then remove them afterwards anyway, so you can just build a Docker image. If you do so, I suggest that you build it now because it will take a little bit, so it should be done when we are at the hands-on session. So this hour will look like, I'll start with some basic theoretical background, so what are collaborative-SNARKs, why we need them, and what is our tooling doing. Afterwards, if everyone is set up, we'll get into some more practical stuff, and I'll show you how to build a collaborative-SNARK based on Circom, and afterwards we'll build one on Noir. I'll see how much, as I think the presentation will take approximately 20 minutes, and afterwards again 20 minutes, so we'll see how fast we can push the hour, but yeah, maybe we have some 10 minutes or so at the end of it to chat a little bit, or if you have any more questions. So is everyone seen it? Okay, I think the QR code will show up later once more, so it's not off the word, but yeah, I suggest to build the Docker now. So in the meantime, I've dropped the word collaborative-SNARKs or co-SNARKs now once or twice, so maybe some of you need to get some introductions what this actually means. And for that, I'll borrow a really basic example that's used usually in the MPC setting. So I don't know if you're familiar, that's, yeah, as I said, a really old problem to explain what MPC can do. It's called the millionaires problem. Imagine you have 2 people, Alice and Bob, and Alice and Bob are in the crypto business, I think, since the 70s or so, and they got some money over this time. And they now want to know who of them is richer. So, yeah, what are the things they can do? The first trivial solution would be Alice just tells Bob, I have X amount of euros, and Bob tells her, I have Y amount of euros. So, of course, they can then check who has more money, but yeah, as the crypto people that Alice and Bob are, and they are pretty influenced by privacy, they don't want to do that, of course. So they don't want to disclose how much money they have, so that's not really an option. Another trivial solution would be to ask their friend, Charlotte, how much to help them. They would just tell her how much money Alice has and how much money Bob has, and at the end of it, Charlotte can just tell them, yeah, Alice is richer. But also, this is, of course, not really a solution because they need to tell the net worth to somebody, to some trusted party, and they also don't want to do that. So that's private information that they want to keep secret. So what can we do? In comes multi-party computation. I'll give you a small wrap-up about MPC. It could be a little bit boring for some of you if you're already familiar, but still, I think we're at the ZK Summit, not the MPC Summit, so I think I should do that. So the MPC is based on a technology or idea. It's called secret sharing. It was introduced from Shamir in his famous paper, How to Share a Secret, in the 70s, I think. And the problem that it wants to solve is, imagine you have a secret X and you want to share it to some parties. How you do that with Shamir secret sharing is you take a polynomial of degree D, where you set f from 0 to your secret. Okay? So from that polynomial that you then have, you sample n points and send them to n parties, to n different parties. From high school math, we know that if you want to reproduce a polynomial of degree d, you need d plus 1 points, which is usually called the threshold t then. So in order to reconstruct the polynomial, you need to get t points, so d plus 1 points, then you can reconstruct the polynomial, set it to 0, and get your x back. This threshold T is also in MPC protocols usually the number of parties that are allowed to collude. So that's also the higher the degree is, the more secure it is, so the more people need to collude. Really basic idea. The other thing that's another secret sharing idea protocol that's usually used is called additive secret sharing. We can even go back to grad school math here. You have your secret X and split it in n parts, such that the sum of those shares is again your secret. So you have to split, as you send then the shares to n parties, and we can also trivially see that if you want to reconstruct the secret, you have to gather all your points again. So for Shamir secret sharing, you can split it up to T, you only need T points out of n, and for additive secret sharing, you need all parts again. So now that we know how we can share a secret, can we also compute on secrets? The answer is yes. And for the remaining talk, I usually talk about additive secret sharing because I think it's a little bit easier to grasp. It's just basic addition. And I'm also using free parties because it's a very common use case, a very common setup that you have free parties. So that's for the rest of the slides. So if we want to add two secrets, X and Y, we split them up in three parts and send them to two different parties. So if we want to add X and Y, we can trivially add, so each party just adds their shares. So if party 1 adds X1 and Y1, party 2, X2 and Y2, and so on. And from there, we can also trivially see from basic grad school math that then, if you reconstruct those added shares, you get the share of X times Y. So that's super cool. So this means for additions, we actually don't need to perform any more work as you would do on a single machine. It's like if you want to add X and Y, you just add them, and that's the same for the MPC of the computing parties. They just need to perform a simple addition, and they get the secret shared value of X and Y. So that's super cool. Now about multiplications, we can see here that we can't simply multiply X1 times Y1 because then we don't get the secret shared value of X times Y. It doesn't work, so we need to think about something different. So usually how to do it, there are multiple approaches. I give to you two of them. The one that's very commonly used is based on beaver trippers, where you generate some helper trippers, usually in some offline phase, where you have three values from which you know that A times B equals to C, and the A, B, and C are secret shared for all parties. As some small notation also, if you see a value in the brackets, it means this value is secret shared. What you're doing now is engage in some protocol. It's a really simple thing. If you want to write it down on paper, you see that after you did those two steps, I won't get into detail about the formula, that's not so important, you see that you get a secret shared value of X times Y. The important part is you have to open some points of some values. When we talk about open, this means we send the shares around that all parties can reconstruct the point. So there is some communication involved. The other thing that we are also heavily use are replicated secret sharing protocols. For the free party setting, this is then called a 2 out of 3 sharing, where you, so based on additive secret sharing again. And this means if at the beginning of the protocol, every party gets, the three parties each gets their share, and then send their share to the next party. So party 2 has the share of party 1 and party 2, and so on. This doesn't break security, doesn't break anything, doesn't break privacy, because of course we know that we have to get all n shares to reconstruct the secret. And then they engage in this, so they compute this small formula down there. And afterwards, as they need to send, as everyone has to have 2 shares, we have to send our share that we just computed with this formula to the next party. So what is the takeaway? You don't need to memorize all this formula. I just wanted to show that for nonlinear operations, there is some form of networking involved. So if you have a linear operation, think addition, parties compute locally on their shares, there is no additional overhead involved. It's just like for a single party. Just a single machine. And for nonlinear operations, parties need to communicate. So there is some networking involved. That are the key takeaways. You don't have to remember all the other stuff, actually. So okay, now we know we can do additions and multiplications. And to borrow some lingo from ZK, you can build then you can build arithmetic circuits with additions and multiplications. And as soon as you can build something as an arithmetic circuit, you can also do an MPC about it. So you can engage an MPC protocol that evaluates that circuit. And we know from ZK we can actually do quite a lot with arithmetic circuits. So back to our problem. Now Alice and Bob, they know about MPC, of course, and they engage now in an MPC protocol where they share their values x and y to some MPC network, some machines. They can be part of the computation, but they don't have to be necessarily. Depends on the use case, but they can also compute, but they don't have to. Send that to the MPC protocol, to the MPC machines, and the computing nodes then tell us, okay, Alice is richer. So everything is fine, nobody learned anything, and we're good to go. To sum things up, Alice and Bob are two distrusting parties. They have a private information, which is their net worth, and they don't want to tell this to anyone else. So they engage in an MPC protocol to see who's richer. Everything is fine. But if you think about it, what is the problem here? So imagine there's another person again, Charlotte, and she also wants to know who is richer. So now the MPC protocol tells her, okay, Alice is richer, and she asks, is this really true? And she can't really know that. So I'm leaving a little bit of stuff out here. It's like really condensed, but only usually parties involved know what they computed and whether they behaved honestly. So if Charlotte also wants to know if Alice is richer, she has to trust Alice and Bob or the computing network. So she can't just verify that. So yeah, what now can we do? We can think about zero knowledge proofs as we had the ZK Summit. What can we do with zkSNARKs? zkSNARKs usually are used to prove to Charlotte, sorry, that some computation was done correctly. But yeah, I won't get into details about zkSNARKs as we are in the ZK Summit. I think every one of you is very familiar with how they work. But yeah, if we want to think about the problem, it does not work to solve it with zkSNARKs because we are back at square one again, right? Because you have to compute the ZK proof again, so you have to have the access to x and y, so to the net worth of Alice and Bob. So yeah, who computes the proof? You can outsource it, but then again, the person computing the proof knows the values. So we're back at square one. But I wanted to know, keep in mind, if you talk about zkSNARKs, they can do a succinct proof for computational integrity. So it can verify some computation that was done in a very easy, succinct way, and potentially keep secret input hidden. I say potentially because everyone is talking about ZKPs, but for the scalability, we actually don't need the ZK part. So we potentially want to have some secrets hidden, but for our case, we want it also. So now we have these two cool technologies, zero knowledge that can prove some computation, and MPC where you can engage in a protocol where you don't disclose your private information. So what happens if we combine them? We get collaborative-SNARKs. So I've been told this should be an interactive workshop. So I talked a lot now. Has anyone any questions so far? Okay, perfect. So what are collaborative-SNARKs now? If we combine the two technologies, it now allows multiple distrusting parties to jointly compute a proof. So basically, we verify that an MPC computation was done correctly. And how we do that is execute the ZK prover in an MPC circuit. If you remember, if we can do an arithmetic circuit out of it, we can also do an MPC program. So this also includes, of course, zero-knowledge proof systems like ROS16 or whatever. So how does this transform the problem? Now we have, again, the millionaires problem. Alice and Bob secret share their values, send it to the computing network. And now the computing network says Alice is richer, and here's a proof that Alice is richer. So Charlotte just takes the proof, verifies it locally on her machine, and knows, okay, wow, Alice is in fact richer. So as we're doing ZK inside MPC, you may think about some performance penalties because doing a ZK proof about a statement is already quite complex, and also if we transform a problem with MPC, it's it usually rises in complexity. So the cool thing about this is that most ZK proof systems heavily rely on fast Fourier transformations and multiscalar multiplications. It's the bunch of the work, it's a whole lot of the work that is usually done, and those operations are highly linear. And if you remember from the introduction, linear operation doesn't impose additional overhead if we do MPC. So the FFTs and MSMs you're doing in collaborative SNARKs actually take the same time as you would do on a singular machine. You can just compute your FFT and the MSMs on your local shares, and at the end of it, you get a secret shared value of the FFTs and MSMs. So that's super cool. You don't have to do anything additional. You do the same thing as a single prover. What's also cool is then if sometimes ZK hardware comes around, soon TM, then you can use those technology, you can use the hardware to run FFTs and MSM also there. So we actually, in collaborative SNARKs, we also profit from the hardware acceleration. What about nonlinear operations? Remember, for multiplications and stuff like that, we need to communicate. So what's not so nice are large multiplications. In a lot of proof systems, there is sometimes we have to perform these really large vector multiplications, sometimes to the domain size, which sometimes get 2 to the power of x, which is there's some limitations here. We need to send those around. You can do some tricks, but at the end of the day, there is some overhead involved there. And also the hash-based hash-based polynomial commitment schemes are not so nice. So the SNARKs usually, people call them, like all this Fry-based stuff, because it's based on hashes, and hashes are inherently nonlinear. That's their whole point. So it's actually not so nice for collaborative SNARKs. For collaborative SNARKs. So to build an efficient collaborative SNARKs, I'd say it's still an open topic. There are some tricks you can do also here, but it usually comes at the cost of the verifier performance, and so yeah, it's another rabbit hole. But everything that's based on elliptic curve, as well like KCG commitment schemes, that's super nice. I'm getting ahead of myself a little bit here, but I didn't talk about our tooling so far, but there's just some benchmarks that we did from our tooling. So I don't know if you're familiar with Circom, but there's like these two provers from Circom, SNARKJS and RabbitSNARK. And if you see the blue line, that's the performance of our tooling. So you can see that our tooling is actually faster than the SNARKJS one, even though we are doing MPC. So there are multiple reasons for that. First one, we're using Rust, and they're using JavaScript, and Rust is blazingly fast, so we just are a little bit faster than them. The other one is RabbitSNARK, which is based on C++. You see that's just RabbitSNARK is still a lot faster than our tooling, but yeah, we'll see how fast we can actually get, how close we can get to RabbitSNARK, because this was the first iteration of our tooling. We rewrote everything over the last couple of weeks, so actually there are no new performance numbers so far, but I think we'll close the gap a little bit. But yeah, we'll see. But at the moment, also, sorry.
Are you multi-party where there are single proofs as well, or are you like 3xing or something the singles?
Yeah. So the question was if they are using single parties and we are multiple parties. Yes, we are doing this is based on a replicated secret sharing model on three nodes with networking involved, and they are using a single prover in JavaScript. Yeah.
I suppose that in Co-Circom, you said you rewrote everything in Rust. So you also rewrote the Growth 16 SNARK. It would be maybe interesting to see in this graph what would take your ZK SNARK prover, how much it would take, because then you could see what is the collaborative MPC overhead, for example, because maybe your prover is also slower than RabbitSNARK. You know, so I mean, then you would get a clean overview of like what is the overhead.
I won't repeat that question because it was rather long. Sorry,
yeah.
But it's just different benchmarks. There's also we tried to do some benchmarks on a single prover that we see how much our implementation takes actually, and because it's really hard to benchmark MPC usually because you're on distributed machines, so you have just only the timing. So that's not as easy. You can't just take chunks out of it, and then I could say our FFT implementation is way faster than the one from SNARKJS. I could say that, but it's still relevant how much the whole steps with the communication involved is how much this takes, and that's usually quite hard to do with MPC because as you're in a distributed setting. but yeah, I mean, yeah, we'll think. So there will be new performance numbers rather shortly, and yeah, I mean, there's this. We based on the Graph16 prover from Arcworks. I don't know if you're familiar with that. So we're based on that one. So there are benchmarks for there on the single machine, but usually the overhead involved is for Graph16. It's actually quite nice. There's just one round of communication, so it's not that hard. Okay. So what are the use cases? We usually think about two big use cases. The first one we talked about already. We call it compute on private shared state. We want to, like the example from Alice and Bob, if you know privacy blockchains like Alio and Adstack, they want to allow people to compute on private state in contrast to Ethereum where everything is public. But what you can do is compute on multiple private states. You can write dApps that are running on, that are based on your private state, but they can't write an application that is based on multiple private states. So that's the first use case. We have all benefits of succinct proofs because from the view of the verifier doesn't realize that there is a collaborative SNARK or as ordinary zk-SNARK because the proof at the end of it is just the same. So the verifier doesn't know, so we get all benefits of the succinct proofs. And the other one is private proof delegation, where imagine you have a limited piece of hardware like your mobile phone and you want to compute the proof. Yeah, that's usually if the proof gets rather large, it's really hard. So you can use MPC or to the collaborative-SNARKs to build, you secret share your witness, send it to an prover network, to a network that computes the proof for you and send it back to you. So you don't have to, you lose no privacy because you secret share your private input and just compute the proof outside of your machine. So that are the two use cases that we are looking into at the moment. And so that's it for the theoretical thing. Here's again the QR code. I think nobody joined so far, so I think we are good to go. So I talked a lot about the theoretical stuff now. So what were we building? So TACEO over the last couple of months, we started with building collaborative SNARKs based on Circom. Circom is a very well suited language for that because it's really small and also the SNARK.js is not that feature rich. It has Graph16 plonk and flonk. But yeah, it was a really good starting point. But now we also started, now that we are pretty done with Circom, we went on with Co-Noir. So it's still called Co-Circom, but this will change in the future. So what is Co-Circom? Co-Circom, as I already said, is you can build collaborative SNARKs based on Circom circuits and Noir. We have support for Graph16 and plonk for Circom, and we are using the honk prover for Adstack, for Noir. And the really cool thing is with this approach, as I said, the verifier cannot distinguish between a collaborative SNARK and a zk-SNARK. So we can utilize the whole toolchain that is already written for Circom and Noir, which means we also get an EVM verifier for free, so to say. That's nothing that we have to do, you have to work with. So it just works. It's just if you verify SNARK.js, if you verify your proof with SNARK.js, it works. If you verify the proof with our prover, that works. So there's no difference. So that's really cool. And it's also already usable. We showed this at ETC, I think. We had this demonstration project. We called it a Max Pick Challenge, where we wanted to show that we can actually build tools now with collaborative Circom, with Co-Circom. The idea was we make a game where everyone that wants to participate has to guess a number between 1 and 1,000, and the highest unique guess wins. So this means if I bet 999 and some other people also said 999, it cancels each other out, and the guess is disabled. So of course we can't do that with usual blockchains, because if you write it on chain, everything is, you see every result, so you could just cheat, see what's the highest value, or someone could just snipe your result, so that obviously doesn't work. So we built this with collaborative Circom, where we then have the guesses were kept private, and then you compute at the end of it, compute a big circuit, and then you roll it on chain. And it's fully deployed on Optimism. We used the SNARK.js verifier, and everything worked quite well. That was really cool. once more, I think we don't need it, but I wanted to make sure that everyone can scan it. So again, any questions so far? Yeah?
A very detailed question about the problem you just mentioned. Can you copy inputs? Are you protecting against Alice and Bob and other people from voting the same way? I'm guessing.
In the Max Peak challenge?
Like,
so,
I cancel somebody else's out by guessing they're going to guess 911 and then use an identity and then throw in a 999 and then push the result down somewhere I want to.
and the question was if we protected for some replay attacks, I think. In this scenario, it's like in this specific setting we also broke a little bit with the idea of MPC because every node was hosted at our place, so it was like for demonstration. But there was actually quite involved how to protect the guesses. You have to commit to the guess in the beginning, so and then write the commit on chain with some secret randomness that you chose on your machine. So if you chose 99991, you also computed some random values in your browser, computed the Poseidon hash, sent that on chain, and then we only stored the Poseidon hash, and then so you are nobody learned anything about what you were guessing, so you can't, because there's the randomness involved, you can't just guess from the commitments what was guessing there already.
And I can't commit to somebody else's.
Yeah, you can't, because you have no idea. Yeah. Mm-hmm. So we go now pretty shortly to the technical thing. I think that's also good to know what the workflow looks like when you build a collaborative-SNARKs. It's easy to see it in the beginning. So there's necessary steps to build the collaborative-SNARKs. Imagine we have Alice and Bob again. The first thing they need to do is secret share their values. So again, they're split it up in 3 parties with additive shares. So secret share your input. Then you send your shares and the Circom file or the Circom circuit or whatever that you want to compute, you send to some computing network. Again, as a party A and B could be part of it, but they don't necessarily have to. So you send your shares to the network. So if you zoom in a network, now it looks like that. Party 0 has access to A0 and B0 and so on and so forth. What they're doing now, we usually call the extended witness generation. This means you actually have to evaluate the Circom circuit. So that's the step where you, when you look at your Circom file, you actually have to run through it, you have to compute it, that you get your extended witness. So they do that in an MPC protocol, and that's actually the step that for MPC takes the longest. So the prover is way, way, way faster than that. And computing the extended witness in MPC, you can do that with Co-Circom, but the imposed overhead here is really large because it's just basically a general purpose MPC VM because you just write any program. So you have to engage in, So that's the step that's at the moment is the bottleneck by far. But you have to engage in MPC protocol, execute the Circom file, circuit, and you get a secret shared witness. Then, it's like that. And at the end of it, they engage again in an MPC protocol, and then you get a collaborative-SNARK. So that are the steps necessary to build a collaborative-SNARK. Okay, we're going now to some examples. I think I'll sit down for that. Hope it works. So I don't know, has anyone problems with the Docker installation, or is everyone good to go? Because I had once a problem. It didn't reappear, so I was scared that it will happen now. But I think, okay, everyone good? Okay, you can see my screen, right? So I'll also check out the project. So the idea what I will do now is there's this README also. I don't know if you've read through it a little bit, but I'll show you how to build your collaborative SNARK now, first with a Circom example and then with the Noir one. Oh, wow. Okay. The first thing we're doing is we go to the Circom folder and check out what problem we want to solve actually. I'll show you the circuit. It's here. So if you're in the Docker now, there's no Vim or Nano installed. If you want to check out the Circom file, I've installed bat, so you can just write bat millionaires problem.circom. It's a really cool tool. I recommend it. But yeah, if you, but so you can inspect it. We can see it also on the screen. It's, again, this millionaires problem. Also, this is not a Circom introduction, so if you're not familiar with Circom, you have to believe me that this is doing what I say it does, because I don't want to get into details too much, because it's, yeah, as I said, there are a lot of cool Circom and Noir examples out there, introductions that are way better than whatever I could come up with in this next 20 minutes. Also, if you have any question, if something doesn't work, just raise your hand, maybe we can figure it out. But what we're doing, we have two inputs, Alice and Bob, that are that are private inputs for the problem, and one output, which is the result. And we want that if they have the same money, we get a 0 result. If they have the same, if Alice is richer, we get 1, and if Bob is richer, we get 2. We do that by first including some utility functionality from the Circom library, standard library, unofficial, I guess, but yeah, there's some cool utility functions there. First is to check if the values are equal. So we get, in this value, we get 1 if the values are equal, and we inverse the result. As remember, we want the result to be 0 if they have the same money. Afterwards, we check whether Alice has less money than Bob, and increment the result by 1. So if Alice has less money, then this value is 0. Okay, I'm getting confused now, and then we increase it, so we get 1 for Alice and 2 for Bob. And then we multiply the two things. This is 0 if the equal amount of money, so it just develops to 0, and 1 if the same amount, and then we get the value from the less than operation. So nothing really complex going on here. README. It was in the wrong folder. Okay. We go again in this folder with the millionaires problem, and the first thing we need to do is compile the Circom file. We do that by, it's in the README. In the README, you can copy this command. I also prepared a just file. I don't know if it's a command runner that's also already installed in the Docker, because later the commands are actually quite convoluted because we have to engage in an MPC protocol. So there is usually 3 processes involved, and it's not so nice to start them in a Docker, so I just prepared a just file that you can run the commands if you want to check them out. So the first thing is we compile the Circom file, so you get some information. We use the Circom compiler for that, so that's not a tool from us, it's from IDEN 3, and it's just a basic Circom compiler. We get this R1CS file. So compile the circuit. The next thing we're doing is we secret share our inputs. In Circom, what you're usually doing if we have 2 inputs like Alice and Bob, you provide a JSON file with the inputs for Alice and Bob. But we can't do that, of course, because we are on 2 different machines. We have Alice put secret shares her input, and Bob secret shares his input. We do that this time with the Co-Circom binary. The Co-Circom binary, if you want to check if it's installed, you can just write it, and there are the commands that are provided. So what we are doing is we split our input. So in a real setting, as I said, this is done on 2 different machines. First on Alice's machine and once on Bob's machine. For the demo, of course, this is on a single machine, but usually this is done on 2 different machines. So Alice wants to split her input. For that, she must define for which circuit. So it's the mil problem Circom file. The input we want to secret share is Alice JSON. The protocol is a replicated free secret sharing protocol. Okay. Replicated free. And the out directory, I've prepared some already. It's secret shared inputs, and we are working on BN254. So we do that, and then the input is secret shared in the correct way. Maybe also if we want to check in the inputs, it's just a basic JSON file where just Alice and some value, and the same goes for Bob. Just some random values I put in there. So we do the same for Bob. I just use the just command for that, so that's a little bit easier. So now in the out, what's it called? Secret shared inputs, you should have 6 files here. It's input from the secret shared input of Alice and the secret shared input of Bob. It's like the 0 indicates that's the secret shared value for party 0. Remember, it's all the Alice stuff is on Alice machine and all the Bob stuff on Bob machine. So, has anyone any problems? Or can we go on? Yeah?
I mean, we don't need to pause for it, but like I have the Docker running, I'm doing this in the Docker, it all works, but I don't have the output files, so I don't know where.
Okay, can you try with the just file?
I did it also with the just file, so
Okay.
but I don't see the.
Has anyone else this problem?
Directory called out.
It's writing in some. Okay, right here. Okay, got it.
Okay, perfect.
I don't see there.
Oh, good, good. Okay, yeah, we have these 6 output files, and then we can go on. In a real setting, Alice would send the shares to the respective parties, and Bob would do the same. What we have to do now is maybe a little bit counterintuitive if you think about it in the first point, but as we are using the Circom toolchain, we're using the Circom compiler also. So they need to get their input in a specific way, such that usually you have Alice and Bob in the same JSON file, but now they get it from different sources. So we have to merge this input together, but this merge is not a reconstruction of so there's no opening word, it's just party 0 takes the input from Alice and the input from Bob and merges it in a single file. So there is no necessary MPC thing, it's just like copying the files together, so there's one single input. We do this with the merge input shares command. The inputs are then the secret shared input, and for Alice shares, that's a little bit so secret shared, and then the input from Bob. We again use this replicated free secret sharing and inputs. And the same curve. I hope I didn't do a typo. You see? Yeah, sounds good. So as again, that's done on 3 different machines now, on the 3 MPC machines. And yeah, that's just something you need to do. It's not any complex stuff. It just merges the 2 files. I'm using the just command again, that I don't have to type everything. So now we have merged inputs. We have 3 merged inputs, 1 for each party. Now we have to actually engage in an MPC protocol, as we have to compute the extended witness. So we are set up, every party knows the circuit that we want to evaluate, and it has their secret shared value. So that was, for that, there is, now, if you want to compute that, you need 3 processes for that. As if you start it, there will be the network, the one process that you're starting will open a TLS connection, a server, and waits that someone connects there. So if you want to actually run this program, you either have to copy all of those commands and concatenate them with an AND sign, or you use the just command where it's already done. So I hope this is clear, because this is actually where the processes are sending stuff around. So they communicate with each other by TLS connection. So maybe, have we time for that? Yeah, maybe I'll just show it, because there is also a configuration involved, a TLS configuration. Maybe just very briefly. You have to provide some form of network configuration here, where say on which address you're waiting for a connection, and also what are the certificates of the other parties, and what is your private key and stuff like that. So as said, the communication is all secured with TLS, so you have to provide some form of TLS configuration. So we'll do also that. Just, okay, but I don't remember actually what it's called. Just run witness generation. And as you see, this takes 700 milliseconds approximately, which is rather longish for this program. But yeah, that's the bottleneck that we are actually facing at the moment. So this witness generation. Did it work for everyone? Anyone has any problems? Yeah?
Yeah, problem with all secret shares input about that is not powerful, and they deny to merge it together.
They denied to merge it. You also use the trust commands? And okay, I need to check that out. I don't actually know it. But if you went through the trust commands from top to bottom?
Yeah, like I repeat for you. Check maybe the list was here. But I split.
Yeah, maybe we can check it out afterwards. Yeah. So now we have this generated witness in out witness. So again, some witness for each party. And the last step, of course, is the actual proving. Again, this is an MPC protocol. You can reuse the configuration you had earlier. It's basically the same. It just tells every node where it should wait for communication income and where they should connect to. Also, I think I need to hurry up a bit. So I also run the trust command. We're using Graph16 proof. I think I didn't say that earlier. So we run it, and we see that it was pretty fast. We can also inspect the proof. There is the proof from party 0. They are all the same. It's just, it was crossed wrong. We see it's just some basic JSON file. It's not very formatted, really nice, but it's just the same JSON file you would get if you have done it on a local machine. What you also can see is the public output of the proof. In our case, it was 2. Which we can check, cat input Alice. So that seems right. Bob is richer in this scenario, so the output of the proof was 2. So the result of the whole circuit evaluation was 2. We get a proof for that.
It's just a naming thing that the file is called public input.json.
Yeah, because usually there is no such thing as an output actually in a CK setting, because if you want to verify it, you have to provide the output as public input to the verifier. Okay. So it's usually
just another input.
Yeah, it's another input. So it's like if you say output, it makes sense to reason about it if you execute the program, but in the point of a verifier, it's just another input that you need to provide. So that's, yeah. If you would have public input, it would also be written there.
Okay,
yeah. Sorry, the question was if it's just a naming convention that's if it's that we call this input JSON. Okay, last step is to verify the proof. We can do that either with Co-Circom. Can again write it. Co-Circom verify. We want to prove the proof 0 JSON with this verification key that is already prepared in the Docker, hopefully, and the public input is out proofs public input 0 JSON. We want to prove a Graph16 proof, and we verify Graph16 proof, and then the curve again. Okay, it said it proof verified successfully, and we can just do the same with SNARKs. SNARKs also says this proof is okay. As you can see, from the point of the verifier, there's no distinguish between a collaborative SNARK and the one for if you build it on a single machine. Any questions? Everything worked? Okay. So as I said, the Circom tooling, the formula is pretty done. So there is, of course, as a feature, it's feature complete from our point of view. We could also add this flonk proven verifier, but I think it's not on the roadmap so far. What we are working on at the moment is especially improve the Graph16 performance so that we can actually catch up to RapidSNARK. And also we're investigating how we can speed up the witness extension. Because as I said, that's the big bottleneck. And at least for this private shared state use case, we need a witness extension. For the proof delegation, we don't need it actually, because you can do the witness extension locally in your machine. They are usually not that computationally intensive, so that's not a big problem there. But still, this witness extension takes too long at the moment, and we are investigating how we can improve the performance here. Okay, the other thing I wanted to show you is the same with Noir. So I don't know if people are familiar with Noir, but same as earlier, I don't want to give you a talk about how Noir works. So we're proving this very, very small pocket example. At the moment, we can do with Noir basic field arithmetic, so everything that would involve additions and multiplications from fields, from the native field works. What doesn't work are integer operations and stuff like that. So we are currently trying to, we started on Co-Noir I think 2 months ago, so it's still very, very early, but you can also, we wanted to show that it's already usable in a small sense, so you can do Poseidon hashes and stuff like that. If you want to use integer arithmetic, that's still in development, but I hope we'll finish that it should be done in 1 or 2 months or so, but don't tell my colleagues that I said that, so maybe we'll see how long this will actually take. But still, I wanted to show that you can also do some things with Noir already. So we go to the Poseidon folder. There are some files already prepared. The workflow is pretty much the same as it was for Circom. And we speed run this now because every one of you knows that already. The small differences I will highlight, of course, but the workflow is the same. First thing we do is compile the circuit. So we just write nago compile. Nago is the package manager, I'd say, for Noir. And we compile the circuit. You should then have in the target folder this Poseidon JSON. It's just some artifact that they produced. So we are using, similar as earlier, we use Circom to compile the circuit. Now we use Nago. So you should have this Poseidon JSON file in your target folder. So then we secret share the input again. For Noir, this time we don't have JSON files, but TOML files. So we look at the values. So we want to compute the Poseidon hash of X and Y. So Alice has her Alice TOML and Bob has his Bob TOML where their inputs are written. Then we write just split input. There's a warning there that's from the compiler that we're using. We're basing it on from the compiler from Noir, and the compiler tells us that the one input is missing. So we need the input X and Y, and it sees that, okay, we only provided X. So that's just shows that it's really early in development. That's no problem, but it's just we're using their compiler, and the compiler thinks some things are not there. But as we're in an MPC setting, of course, you only have access to one of the files. So we secret share the input. It should not matter. You should have the secret shared input in this folder. Looks pretty similar as earlier. Now we merge the input. So check it out. Could also be here. Similar step as earlier. Then we generate the witness. Same setup. We have the same networking configuration. Engage in the witness extension that is used in the Noir setting. So Noir is using honk. So they have actually a couple of provers. The one that they want to use as the default prover is the honk prover. It's some variation of hyperplonk. But yeah, we are doing the witness extension for that here. That's actually super fast because we're just doing Poseidon, and Poseidon is, as we know, is super fast in ZK settings. So we have the witnesses here in secret shared form. Then we run the honk prover in a distributed setting. There's some more debug output, and also here the proof finished successfully. So the computation finished successfully. And now there are some additional steps we need to do. As we are using a Plonk variation, we have a universal setup. We have one setup for multiple circuits in contrast to Graph 16 earlier. So we have to extract the verification key from the common reference string that is provided by Rettenberg. We do this with this command. So there's a verification key that is derived for this particular circuit, but it's derived from the common reference string that we have that we got from Rettenberg. Rettenberg is the proof system of Noir. So we extract, we create the verification key for that circuit, and now we can verify the proof. So also here the proof verified successfully. You can also verify these proofs with Barrettenberg, the native proof system of Noir. I did want to add it here because installing Barrettenberg is a little bit bothersome, so I just throw it out. You can do it also if some of you have Barrettenberg installed. You can verify this proof also with Barrettenberg. But yeah, basically, I think I had pretty much end of my talk. So if there's any question, I think it's 5 minutes left, so maybe it took a little bit longer than I expected. So if you have any questions, any problems, please ask me. We can also chat afterwards. There's a break afterwards, so I'm happy to answer some more questions if you have any. And what also would be nice, that's our GitHub repository from collaborative-SNARKs. It would be really nice if you leave a star at our GitHub repository. And yeah, so I'm here to answer some more questions, if there are any. And otherwise, thanks for coming to my workshop. Yeah.
Quick one on, I just tried hacking it. Do you have plans for making this robust for the multi-party protocol?
Yeah, I mean, the next step we want to do is, so if we're somewhat happy with our tooling, the next step we want to do is actually provide a proving network where people can participate and say, okay, we give computation power to the network, where then also get rewards, of course, if you want to compute it. So that's a whole other field that will be done in the next, that we need to investigate in the next couple of months. So that's the next step after our tooling. For the moment, you can use the project as is. You can just run your own machines with the tooling. That should work. We've done that. And yeah, afterwards we need to investigate, especially for the collusion problem that you usually have in such distributed settings when you have an MPC network that just runs. You need to think about what happens if someone with a lot of computational power, a lot of machines, tries to hijack the network. So there's some research needed there, how we can actually do that. But yeah, that's the step for the day after tomorrow, I'd say. Yeah. Any other questions, or did anyone had problems with running through the thing?
I think it worked probably at some point between the Docker processes.
I mean, I can, if they're not.
Just rerunning it.
Yeah.
It's kind of general case analysis. There's ZK and there's FHE. Getting those, like ZK FHE, would be interesting. So do you consider the private proof delegation to be something of a use case rather from that concept, from verifiable FHE?
Yeah, I think a verifiable FHE and this collaborative-SNARKs, or it's also sometimes called publicly auditable MPC. So it's a pretty similar use case actually. There's some distinction, of course, between those two. But I think, it's my personal opinion, but I think if there will be, so FHE, if you want to do verifiable FHE at the moment, you rise in complexity so fast that it's not really usable in any form or means at the moment. And you don't have this problem with collaborative-SNARKs at the moment. So you can do Graph16 proofs and also Plonk proofs, like this EC-based stuff, you can do now in a reasonable amount of time. But if you want to use verifiable FHE, it's like that's more of a thing for in the next couple of years, I think. So if you want to use it today, I think you're bound to use it like that. Sometimes in the future, maybe FHE will be fast enough. Everyone is talking about the hardware acceleration of FHE, but we'll see how long this will actually take and when this will arrive. But if you want to use it at the moment, you're forced to use it like that, I think at least. Also, on the hardware acceleration, as I said, ZK proof system, so I think we get ZK hardware a little bit earlier than FHE hardware, I think, because at least from what I've talked to people, that's not just what I've heard. And we actually benefit from ZK hardware also in the collaborative-SNARKs setting. One thing I have to say about that, for MPC, you're bound, you have an upper limit of how fast you can get, and that's the speed of light, because at one point you have to communicate. So you can't just throw hardware on the problem, because there is this limitation. There will be networking involved, which is not the same for FHE. So theoretically, if there will be fast enough FHE hardware, you will, at some point in the far future, maybe you are faster than the MPC setting. But I think this will take a lot of time if it happens actually. So yeah.
So this can be used both for collaborating on as a marketplace for SNARKs, right? You can use providing compute power. I'm thinking of the Noir context specifically, and also it's useful for building applications like maybe like a dark pool kind of application that requires, right? Like this library is useful for both types of things.
Yeah, the question was in which use cases we are actually thinking. I forgot to restate the questions earlier, so sorry about that. So the question was whether for the use cases. But yeah, actually the use cases are exactly what you provided. So the private dark pool setting is something Renegade is doing. I think they're doing it with collaborative-SNARKs. So that's one big use case, and the other one is the proof delegation when you want with privacy witness. So if you don't need privacy for your witness, you don't have to engage in that problem. You can just use any proof market out there. But if you want to keep your private witness hidden, you need to engage in this protocol. Yeah, I think we are pretty much out of time.
One last question, is it?
Okay, if anyone has one question, then doesn't seem like it. Yeah, then thanks again. And yeah, if you want to chat, I will be here. I will be around. So thanks.